Hens love roosters, geese love ganders, everyone else loves Ned Flanders.
Not me.
Everyone who counts loves Ned Flanders.
All right, everybody, welcome to the notes on 7-2. We're going to talk about properties of exponential functions today, okay? So far, we've at least talked about them, we've introduced them. We're going to pay no attention to this objective because we're not going to talk about base E, which is good because it's less. We're going to look at properties of the actual exponential function y equals ab to the x power. So, essential understanding: the factor in a in y equals ab to the x can stretch or compress and possibly reflect the graph of the parent function, which is just y equals bx. This stretch and compress, this is nothing new for us. We've been stretching and compressing different graphs all year, so hopefully this doesn't seem like a novel concept. But if we look at, for example, in the drawing here, in the picture, y equals 3 times 2 to the x stretches the parent function of y equals 2 to the x by a factor of 3. So if this first red one right here, if this were y equals 2 to the x power, then when we stretch it by 3, where, this was 2, 4, so now it's 2, 12. This was 1, 2, so now it's 1, 6. Pretty self-explanatory stuff there. How to graph these? How does the graph of y equals negative 1/3 times 3x compare to that of the parent function? So the easiest way to look at it is just to make a table of values. You can do this by hand, or you can do it in your calculator. We've been practicing doing that in our calculator some. So each value now is negative 1/3 times the corresponding value of the parent function. So what we do is we look at the parent function with whatever value we have there, and then we look at, well, what does it look like now that we're multiplying each thing by negative 1/3? Pretty self-explanatory stuff here. Let's take a look at how does the graph of y equals negative 0.5 times 5x compare to the graph of the parent function, which is y equals 5x. So you can graph these and look at them, but I don't really need the graph. I really just want to know from you, could you describe it? Similar to this description here, the negative 1/3 in y equals negative 1/3 reflects the graph, and it compresses it by a factor of 1/3. The domain and the asymptote remain the same. The y-intercept becomes negative 1/3, and the range becomes y is less than 0. So if you could talk about domain, range, asymptotes, and compression or stretch, that would be great. If you could pause the video here and do that. Go ahead and pause the video now. Okay, so the answers here, and if you graphed it, that's great. We can talk about the graph in class, but hopefully you're doing that on your calculator or just a quick sketch. It reflects it across the x-axis, so this has been reflected, the new graph, across the x. Okay. It has also been compressed by a factor of 1/2. And then everything else that was listed up here is true. The range is now y is less than 0. The x-axis is still an asymptote, and the domain is the same. Okay. If that doesn't make any sense, make sure you make note of it, and we'll look at the graphs in class on your calculator and on the board and make sure that everybody's squared away. But really, if you put these two graphs in your calculator, you're going to see these differences pretty simply. We can shift things horizontally. A horizontal shift, actually let's move this up so you can see. A horizontal shift, y equals AB, that's too dark. Y equals AB. Yikes. Y equals AB to the x minus h is the same as a vertical stretch or compression. Y equals AB to the negative h inside, and then b to the x on the outside. Okay. A vertical shift, y equals AB to the x plus k, also shifts the horizontal asymptote from y equals 0 to y equals k. So, right, very wordy there. We've been talking about h and k and stuff like that all year. So if we look at a couple of examples, this might make a little bit more sense. All right. So translating the parent function y equals bx. So say we have y equals 2 to the x minus 4. So we make a table of values. You just pick some numbers, put them in for x, pick some more numbers, get some numbers out, and we look at it and see, oh, okay, it's the parent function y equals 2x, that's this red one right here, but everything has been shifted 4 units to the right. Okay? Really no big deal. This inside the parentheses of the exponent is the horizontal shift, and this is the one that's counterintuitive. So when it's minus, it goes in the positive direction. When it's plus, it goes in the negative direction. Okay. The asymptote remains y equals 0. The y-intercept changes. So you know that's a thing. But other than that, no biggie. Okay. Let's take a look at another example here. So here we have y equals 20 times 1/2 to the x plus 10. Some people are probably wondering, well, why don't we just write y equals 10 to the x, because half of 20 is 10. The reason is order of operations, guys. This, we have to do the exponent first. So don't do that. That's bad. Don't do that. Okay, let's just erase. So first, you know, you make a table of values. You put in some numbers for x. You get some numbers out. So we look at what that looks like. This is a decay. It's going down because this is between 0 and 1. And then it's been shifted up 10. Okay? It's been shifted 10 units up. All right? So here's the original, and then here it is, shifted 10 units up. Okay, and then the plus 10 there, that's the translation we're talking about. It also translates the asymptote. So the asymptote, instead of being the x-axis, is now the line y equals 10. The y-intercept becomes 30. The range becomes everything greater than 10. The domain is the same. Okay, you can use a graphing calculator to check this, and we get the same exact thing we did when we did it by hand. Here's the table giving us the same values that we had right here. Okay. And it actually, you know, it'll keep giving us more values if we want. All right. And actually, sorry, this table, these aren't the same values. This table was graphing this, and then we shifted it. So these are all plus 10 here, if that doesn't make any sense. This table is just for this function. We added the plus 10, so this would be on this graph negative 150, 0, 30, 120, 215. So it's each one of these plus the 10. Okay. Take a second and try and get some graphs here for number 2. How does the graph of each function compare to the graph of, to the graph of the parent? You can graph them and look at them. I'm not really interested in your graphs as the answer. Those we can generate on our calculator pretty easy. I'm more interested in, do you understand what's going on? Can you describe it? Okay, so pause the video here. See if you can describe how each of these is different than its parent function. Okay, let's take a look at what you got. 2a, it's been translated 2 units to the left. The y-intercept becomes 16. So 2 units left, and y-intercept equals 16. Everything else is the same as the parent function. So we're comparing y equals 4 to the x and y equals 4 to the x plus 2. Okay. Here we're going to compare y equals, hopefully you already did compare, y equals 0.25 to the x, and then y equals 5 times 0.25 to the x plus 5. So how is that one different? Hopefully you wrote something down along the lines of it stretched the graph. It stretched it by a factor of 5, so it's been stretched. Hopefully you wrote down the fact that it's been translated up 5 units. Okay, stretched and translated up 5 units. Again, if you want to look at pictures of these, I think graphing them is a good idea. We'll look at our graphing calculators in class and make sure we know how to do that. All right. Some concept, basic stuff. The parent function is always this, y equals b to the x. Okay, this a value is going to stretch or compress. And then if it's negative, it's going to reflect it in the x-axis. That's where it turns it upside down. Translations, horizontal translations by h, vertical by k. And then when we combine them into one, it looks like that, all of them all at once. Okay. Using an exponential model, so word problems, the best temperature to brew coffee is between 195 and 205 degrees. The table shows temperature readings from a sample cup of coffee. How long does it take for a cup of coffee to be cool enough to drink? Use an exponential model. So first we have to know a set of values and the best serving temperature. We have the best serving temperature. Time it takes a cup of coffee to become cool enough to drink, and then an exponential model. So at 0 minutes, it was this temperature, 5, it was this, 10, this, 15, and so on. It keeps getting cooler and cooler, obviously. So we plot the data to determine if an exponential model is realistic. Okay. Because it is kind of going down and then starting to curve, that looks like an exponential model. The graphing calculator exponential model assumes the asymptote is y equals 0. Since room temperature is about 68 degrees, we subtract 68 from each temperature value. Calculate the third list by letting L3 equal L2. We'll talk about how to do that in your graphing calculator and why you need to do that. But we're not assuming 0 because it's not going to get down to 0 degrees. This explains to you exactly how to do an exponential regression in your calculator, and we'll work on that specifically in class if you can't figure it out. But it's your regression menu, and then you're going to choose exponential. It shouldn't be too hard. The directions on this page are for a TI. If you have a Casio and you go to the stat menu, once you've put all your numbers in, if you go to calculate and then F3 right here for regression, if you scroll over one, you'll see exponential as a category. Now, obviously, it's not going to do it because I don't have any numbers in. But you can put those numbers in and try, and then we'll walk through how to do it in your calculator if you can't figure it out from that. But we'll practice the calculator stuff in class. Use an exponential model to determine how long it would take for the coffee to reach a temperature of 100 degrees. Okay, and then in problem 3, would the model of the exponential data be useful if you did not translate the data by 68 units? So would this, if we didn't do the 68, would it be useful? And how long for it to be 100? Take a second, pause the video, get some answers to that, and then we'll talk. All right, you've got some answers. To reach about 31 degrees, to reach 100 degrees, it's going to take about 31.9 minutes, so about 32 minutes. And then as far as if we didn't translate by 68, would it make sense? No. Hot coffee cannot cool below room temperature. So if I have a cup of coffee in my classroom, if I let it sit for 2 days, it's still not going to get colder than the temperature of the room, which some of you would argue is close to 0, but it's not. So it's important that to use exponential data, we have to translate the data by 68 units. So we have to come up, if you say the room is 70 degrees or whatever it is, the data is not useful unless we do this translation. Okay? That's it for the notes. Make sure you bring your calculators next time so we can everybody can get an exponential regression. Practice with that, and I will see you then.